In the last video, we have seen the comparative study on basicity. So here, obviously, we are going to discuss just the opposite one, the comparative study of acidity. So in case of comparative study of acidity, the conjugate base factor, or after losing the H plus ion, the conjugate base, how it is going to be stabilized. This factor will be the key factor in most of the problems that we used to face in JEE mains and NEET exams. So the process will be of this particular lecture will be like this. First we will solve 4-5 standard problems, then I will give you assignments. I have seen few comments on the previous video where you have pointed out the answers. You do check it out where it was correct and where it is wrong. I have mentioned it over there. Start of today's discussion with this problem. 4 options are given. You see it carefully. All of them are organic acids. The question is, we have to find out the acid which is having smallest dissociation constant. That means obviously smaller is the dissociation constant, weakest will be the acid, the least will be the acidic nature. So that we have to find out. So let us see. To understand this, we will be using this conjugate acid base theory. What is that? If I take HA, suppose this is the acid, it can dissociate into H plus and A minus. Now this much, after losing H plus, we know it is the conjugate base. If it is stable, corresponding acid will be the stronger acid. Based on this principle, we are going to find out of these 4 which one will be least acidic. Let's see. Now if we analyze the structure and the electronic effect, let us see. So in the first option, so there is CH3 bond CH bond C double bond O, single bond O minus. Minus because H plus we have already removed. We are talking about the conjugate base. And over here NO2 group is attached. Now what happens? Since the NO2 group is having the capability of withdrawing the electron, that is minus R effect. So what happens is that there is a general tendency of drifting of electrons. See, minus A minus R is same actually. So there is a general tendency of drifting of electron away from this oxygen, and it gives the conjugate base kind of stabilization. This is option 1. Let us see the next option. Option B, that is, here you see CH2 bond CH2 bond C double bond O, single bond O minus. Same here also we are talking about the conjugate base. On this side we have the NO2 group present. So the position of the NO2 group is different over here. So NO2 group similarly will have the minus A or minus R effect, whatever you say. It is having the tendency of withdrawing the electron. Drastically it can withdraw. So it will also, as you can see here, the drifting of electrons. So here also the stabilization will be there. Now let us see the next option. Here we will have option C, Cl. There is a Cl actually, CH2 bond CH2. On this side there is C double bond O, single bond O minus. On the other side we are having Cl. Now chloro, it is having obviously the minus I effect. It can drag the electron on its side because of its electronegativity. But see, minus I is weak. The effect of dragging the electron is not as strong as is compared to the withdrawal of electron. As we have written, minus I is lesser than minus R. So here also the conjugate base will be stabilized, but comparatively less stabilized. Let us see the last option. Here we are having Cn bond CH2 bond CH2 bond CO2H. That means COO minus. Now Cn similarly is having the ability of withdrawal of electrons, very stronger than the minus I. So this one also will stabilize the conjugate base better than the previous option. So on the first question we have seen this option C, that will be the weakest of the lot. And now let us move on. We'll see the next question. See these 4 options. The question is, out of this, which one will be the strongest of acid? Now let us see the factors which are involved one by one. So let us see this answer, option A. In case of option A, let us draw the structure. It is CH2 bond CH2, single bond C double bond O, single bond O minus we are taking because we are considering the conjugate base. On this side also there is CO2H group. Now on CO2H group there is carbonyl C double bond O, where the carbon is always delta positive, having the deficiency of electron. So the tendency of accepting or dragging the electron on this side will always be there. So it will be somewhat stabilized, but not as good as the others. Let's see why. Next option. Here we are drawing option B, that is CH2 single bond CH2. On one side we are having the CO C double bond O, C single bond O minus because we are talking about the conjugate base. On the other side we are having the fluorine, the electronegative, very strong, most electronegative atom, which will always drag the electron on its side with the help of its strong minus I effect. It's very strong actually, minus I effect, but it's not the withdrawal of electron, it's the dragging of electron. So minus I is always less than minus M, or minus R you can say. Let us see the next option. Here we are having NH3 plus. Now plus charge is there. That means there is a natural electron deficiency on this nitrogen. So it is CH2 bond CH2. This CH2 single bond C double bond O, single bond O minus. So you can see that NH3 plus is present, and due to the presence of this bond, yes, through this bond the electrons will be vigorously dragged, because with the help of a green arrow I have written that the nitrogen will have a very strong electron deficiency, so the negative charge will be dragged and it will be very strong electron withdrawing effect, and the conjugate base will be highly stabilized. So it is going to be the strongest acid out of the lot. The last one, which is CH3 single bond CH2, single bond CH2, single bond C double bond O, single bond O minus, because we are again considering the conjugate base. Now see CH3 group, instead of withdrawing the electron, it donates the electrons, having the plus I effect. So it will not at all stabilizing the conjugate base, which is written already. So option C will be the strongest of the lot. Third question for today is this one. See these options carefully. Here X, Y, it will be Z, and it is W that is given. We have to find out the correct acidic strength order. So all these cases, this OH is common, different substituents. Here the substituent is common, but the position is different, and here Cl is present. We have to find out the correct order of acidic strength from highest, means the strongest acid, to the weakest acid. Let's see. In order to give the answer of this question, we must understand a very basic concept. The main thing is, if I draw the structure, on the aromatic ring there is OH. Let us draw it first. There is OH. Now from oxygen bond hydrogen, oxygen drags the electron, so the H plus will be liberated, as you can see. See this. Let us draw it once again. So there is negative charge on oxygen. So this negative charge, as we know, the phenoxide ion, the negative charge can always come back towards the aromatic ring, and you can see with these arrows the electrons will be circulated throughout the ring and will stabilize the conjugate base. The circulation of electron is there. Now if there is a substituent present alongside this structure, then what happens? Now here I have written X, it's a general denotion, any substituent, X on any position. If X is present, and if you see this arrow, if it withdraws the electron, I'm trying to write, it's very difficult to write like this on these whiteboards with touch. So if X withdraws the electron, then what happens? The electron density is being withdrawn from the ring. So the conjugate base is further stabilized and it increases the acidity strength. Now here you see again the ring is present. Now there is O minus and looking at the question once again, if I draw this C double bond O CH3, here you see the negative charge comes back, and see this conjugation I am talking about. So directly the negative charge goes into the carbonyl, making the oxygen negative, which is a very stable case. So the negative charge on oxygen comes back to the ring and it goes to the oxygen of the carbonyl, which stabilizes the compound. Let us see the option Y, compound Y rather. Here you see there is O minus, means after removal of H plus I am talking about. Then there at meta position there is COCH3 present. Now see, if this negative charge wants to come back, if it comes here, now this double bond wants to be circulated, but where? Can it go inside the COCH3 group? No, there is no direct conjugation present. So the electrons won't go inside the COCH3 group and won't be as stabilized as the previous one because of the position. Let us see the option Z. In case of option Z, OH is there, means O minus I am writing. Then there is C double bond O CH3. So if I want to circulate the negative charge, is there any possibility? Yes, this negative charge will come here. Double bond, yes, double bond goes inside the para position as well, keeping it exceptionally stable, because the circulation, the region of circulation of the electron is much greater compared to the previous examples. The pi conjugation, we can call it extensive pi conjugation. See the amount of area it has covered. Let us see the option number 4, which is W. Here similar structure, but there is Cl, no COCH3. So the negative charge wants to come back to the ring, and the Cl obviously can drag the electron towards itself, making the ring electron deficient, which can drag the electron from the oxygen. That's very good, but it's not as strong as the previous 3 cases.
So from the above discussion, it is very clear that in this case, in Z, because of the circulation of electron throughout this region, this one, the conjugate base will be most stable, followed by this one. So the order will be Z followed by X. Now here also, as we have discussed, there is a minus I effect, but not very strong. Minus I is definitely not as strong as minus R. Here the withdrawal can take place. This group is having a tendency, but this is not in direct conjugation. So it will be not be as stabilized as these two, but compared to W, it will be better. So Y, then W. So this is the correct order.
Fourth question for today is a similar one. Here we have to find out the decreasing order of acid strength. Kindly pause the video and see the options carefully. So there are 3 compounds given. In one there is CH3 group, in another there is NO2, another there is in all the cases the OH group here is a common factor. Here there is no substituent, here there is CH3 and here there is NO2. So let us see what is the correct order of decreasing acid strength. To give the answer of this question, what I am doing is I am drawing 2 structures side by side. It is a very similar concept to the problem that we have last discussed. So I think most of you should be guessing the answer already. So I have written this phenoxide O minus, another one side by side. Now in both the cases the electrons obviously will come back towards the ring, making the conjugate base stabilized one as like this. Now if there is a substituent present here, in blue I have written Z, and with another color if I write, see the position, it can be anywhere. If I write Y, so Z and Y both are not same, or the tendency or the electronic effect is not same. Z, you can see the arrow of electrons, it actually withdraws the electron, so it is actually withdrawing the electron, so it lowers the electron density within the ring. So the ring becomes electron deficient, which further drags the electron on the left hand side from the O minus. On the other side, Y, it donates the electron towards the ring, making the ring electron rich. Inside the ring, the electron density increases, so that negative charge of oxygen will not want to come back towards this ring. That is why on the left hand side, this one will stabilize, this factor, the withdrawal of electron will stabilize the conjugate base. So due to that reason only, if I take this and if there is a CH3 group present, and simultaneously if I draw the other one with whom it is going to compete, that is OH, and on the ortho position there is nitro. So both groups, CH3 and nitro, are completely different. If I talk about the CH3 group, it is having the plus I effect, which donates the electron towards the ring. As we have seen in the previous case, it lowers the acidity. On the other side, NO2 withdraws the electron by means of the resonance effect, that is the minus R. So as we have seen, due to this reason, the third one will be the strongest acid, followed by the first one, because see, here the plus I effect will reduce the tendency of withdrawing the electron as we have discussed, and then the second one. So this is the correct order, 3, 1, then 2. That means option D, that is the correct one.